Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the N-pentenyl glycoside. In short, that is a NPG, means N-pentenyl glycoside. How we can obtain or how we can derive N-pentenyl glycoside by using different starting material that we have seen with the suitable example, as well as when it is formed N-pentenyl glycoside, how it can be used as an donor to get the another derivative which will be biologically important. So that type of the thing we have discussed, and as we know that N-pentenyl glycoside, by taking as a one suitable example, that is a Thai-1 answer rat brain, that is a very big and the complicated molecule, but how it is suitably the architecture or the arrangement of that molecule is how the one atom attached to another one, how that sugar units are joined to each other, and we have learned the retrosynthetic plan for rat brain Thai-1 GPI membrane answer. So, and after that we have discussed regarding this. So today what we are going to discuss, let us look at the board. We are discussing the synthesis of glycosides, and now among that we are now discussing glycosylidine diazerine. First of all, how do we define glycosylidine diazerine, or how we can derive that glycosylidine glycosylidine compound? What are the starting material we are going to consider here for the synthesis of that glycosylidine diazerine? What is the actual structure of that diazerine? What type of the ring or the compound is called as a diazerine, and why it is termed as a glycosidine? So that, and how we can prepare it, and after that we will learn the application of that glycosidine derivative. Glycosylidine diazerine is converted into some another natural or another compound, and which is biologically important. So that type of the study we are going to discuss over there. And now let us see some introduction regarding that. How do we define glycosidine derivative, or what do you mean by glycosidine diazerine? Glycosylidine diazerines are useful as precursors of glycosylidine carbenes, and these cyclic amphiphilic singlet alkoxy carbenes, and as we know that carbene are the electron deficient species, it containing only as a 2 electron and most of the organic reaction intermediate are proceeding via carbons. So that type of the intermediate here also we are going to get, and how it can be act as an donor to get the another derivatives. And these are cyclic amphiphilic singlet alkoxy carbons enable the formation of two bonds at the anomeric center, and everybody knows that the anomeric center, which is very next to the oxygen atom, when we consider next to the oxygen atom, which is a carbon atom which bearing hydroxyl group, when the cyclic form of the sugar unit is concerned, glycosilidine carbene, like other intermediates are reactive and versatile. As we know that are the carbines are very reactive and the versatile in the sense the word itself indicate that, if you remember the diazonium salt, how do we get the diazonium salt? Anybody knows? Yes, diazonium salt will be obtained if the primary amine, for example aniline is there, if that aniline treated with the sodium nitrite in presence of HCl, the reaction condition is kept around 0 to 5 degrees centigrade. In that temperature, that reaction takes place and we will get the formation of the compound is known as a diazonium salt. When the aliphatic compounds, aliphatic amines are there, that aliphatic amine, if you carry out the reaction with the same reagent, the resulting compound obtained will be alcohol. Remember, this is one of the very good reagent to distinguish between primary amines, aromatic amines and the aliphatic primary amines from each other. So primary aliphatic amine gives the alcohol, whereas the same reagent with primary amines, aromatic amines produce or gives diazonium salt. And if that diazonium salt, why it is a versatile, I am trying to explain. The term versatile, variety of the compound we can prepare by using that reagent. Suppose if you treat that diazonium salt with cuprous cyanide, you will get as a cyanobenzene. If you treat the same reagent with Ki potassium iodide, it gives iodobenzene. If it is treated with cuprous chloride, it gives chlorobenzene. If it is treated with water, it gives phenol. So these are, if you treat this compound with beta naphthol, gives orange diester reaction, which is a very fine structure due to the conjugation, or we are getting as a azo compounds. Azo means which containing nitrogen double bond in the organic compound, and they are generally colored compounds, and color compounds are due to the presence of conjugation. So this type of the thing is known as versatile. Now their precursor means the starting material. glycosidine diazerenes, that is 1-az-1,5 anhydroglycitols are thus expected to be useful. So now moving toward the synthesis of glycosidine derivatives. Now we are going to synthesize that one. Synthesis of glycosilidine derivatives, glycosilidine diazerenes. Here the original route depicted in scheme 1 for the synthesis of the benzylated glucosilidine diazerine, which is a 7 number, is still used with the minor variations as evidenced by the preparation of the GLC-N-acimacetyl derived analog. Analog means similar type of the derivatives we can synthesize by using the different starting material, but the resulting compound can be obtained is the same because the procedure is we are going to apply the same. Let's see here how we can derive or how we can obtain glycosilidine diazerenes. Let's see the first compound which I am showing over here. You observe carefully this one, and now here hydroxyl group I am showing that type of the bond. It means that this hydroxyl group, whether it is at alpha position or beta position, that is not assigned, it is present over there. And now the other hydroxyl groups, as we know that they are present at equatorial position, and they are the protected one with benzylic OBN. Here you can write OBN, here also OBN. So this is the structure number first. Observe this structure carefully. What I did, this is a chair form of the glycosides. This is one of the glycosides, where at the anomeric carbon atom bearing hydroxyl group, which is not properly designated, it is shown like this. But when this one compound treated with the reagent number first, I am going to tell you the reagent number 1 later on separately, but when it is treated with the reagent number 1, the structure number 1 further converted into structure number 2. The ring is going to open over here like this. So hydroxyl group over here, then rest of the thing here, double bond NH-OH, not NH, only NOH, oxime type of the derivative we are going to get over here, and rest of the part of this compound we can write as it is. All these protected hydroxyl groups are lying at equatorial position, and they are shown as it is. Look at this, and now this this is a structure number second. This structure number second will be at an equilibrium converted into another structure, that is a ring formation of that structure. So we can show the another structure which is present at an equatorial position. There will be NH-OH group. When rings are formed, these hydroxyl groups attack over there, then NH comes over here and the rest of the groups, but this NH-OH group is lying at a beta position. That is the change we can observe here, and the rest of the groups which are lying at equatorial position, and I am showing all these groups as it is. Look at, this is a structure number, this is a structure number 3 now, right? And now this structure number 3, when treated with the reagent number second, observe this reagent number second. What will be reagent number second? I already told you that just now. I am going to give the name of those reagents list separately after deriving the glycosylidine diazerine. So here this, after adding the reagent number second, what you are going to get? You are going to get the structure number here, this one, here double bond N, and here is a R group. Look at here that the changes, not R, there is a OR. OR means what? Alkoxy group, like this. And now an other part, other group we can show as it is. Here OBN, then OBN at this position, OBN, and this structure is nothing but I am showing this. This is a structure number 4 when R is equal to H. Remember, here observe this structure carefully. I am putting as R is equal to H, that structure number becomes as a 4, and that 4 will be treated with reagent number 3. You will get as a structure number 5 when R is equal to MS. MS means methyl group. So this and that 5 when treated with the reagent number 4th, you are going to get the structure number, you are going to get, this is another structure where here N, look at this structure carefully, there will be a 3-membered ring. Focus only at the anomeric hydroxyl group or the anomeric carbon atom where the changes are occurred. If you observe this structure carefully, at particularly the part of anomeric carbon atom, look at here double bond NOH oxime type, when it get open form as a ring, that becomes as a structure number 3, that is a NH-OH group over there. When it is added the reagent number second, we are getting the changes at this anomeric carbon atom, carbon nitrogen double bond OR, when R is equal to H, that is considered to be the structure number 4, when that structure number 4 treated with the reagents, third, we will get the structure number 5, where R is equal to MS methyl group, and that structure number 5 when treated with the reagent 4, we will get this type. Focus only at this anomeric position, anomeric part. There is a 3-membered ring is formed over here, and other part of the compound, they are remains as it is, OBN, then OBN, then OBN, here OBN, you can write as it is, and this is the structure number 6. And now when this structure number 6 will be treated with structure reagent 5, what do you get? Remember, this structure is going to convert into this structure. Let me show here once again, nitrogen atom here, another. Now observe carefully. Here this NH, there is a removal of hydrogen atom, and instead of that hydrogen atom there is a double bond comes, means 3-membered ring, and this derivative or this type of the compound is known as glycosylidine diazerine. So remember, this is the structure of glycosylidine diazerine. Other part of the compound remains as it is, OBN, then OBN we can write as it is over here. Here also OBN, at this position also OBN, and this is nothing but as a glycosylidine derivative. This is a structure number, this is a structure number, what is this? This is a structure number 7 which we got over here. So when structure number 7, and this is nothing but as a glycosylidine diazerine, glycosylidine diazerine. So that is the structure which we got over here. So remember, now if you see these structures carefully, what you have to remember here, only at anomeric hydroxyl group, anomeric carbon atom, where the changes are occur, and finally there is a 3-membered nitrogen containing double bond species. So that type of the compound is called as a glycosylidine diazerine, and this glycosylidine diazerine can act as an donor or the donor for the further preparation or the synthesis of the other compound. Now let me give you whatever the reagent we have written on the arrows. Now we are going to show over here the arrows, the reagent. I already told you that the reagent I am going to show you separately. So this is a reagent number 1. The reagent number 1 you can remember here, these are the reagents. So reagents, so first one, sodium. As we know that sodium in 96% ethanol, 96% ethanol, which is used for this, and then NH3OHCl, NH3OHCl, and 7 hours at 60 degree. So sodium, which is employed in a 96% ethanol, then ammonium hydroxychloride, that is the structure number 1, is heated at 60 degrees centigrade for 7 hours, and the quantity, whichever quantity they have got, which is variable ratio, this is a variable ratio of 2 and 3. If you observe that scheme, there 2 and 3, where E and Z, that type of the derivative, and calculated yield is obtained 65% to 35%. So that are the yield. Generally we are getting E and Z. As we know that E and Z, these are the new nomenclature system is used for the geometrical isomers. And geometrical isomer, do you know the geometrical isomer? Yes. What is that? Geometrical isomer means the rotation are restricted due to the carbon-carbon double bond, and the isomer gives rise is known as geometrical isomer. And there are the certain condition for geometrical isomer, where the organic compound must contain the carbon-carbon double bond, or carbon-nitrogen double bond, or carbon-oxygen double bond, or carbon-sulfur double bond, and that type of the compound generally shows or generally exhibit geometrical isomers. If you consider, and another essential condition for geometrical isomer, A is equal to B and D is not equal to D, and those fulfilling these criteria, they shows the geometrical isomers. And now here, if you see the simplest structures, suppose as a 2-butene exists in two form, generally cis and trans. And as we know that cis isomer means what? Similar groups are on the same side of the carbon-carbon double bond are termed as a cis isomer, whereas trans isomer means the similar group are opposite to the carbon-carbon double bond are termed as a trans isomer. And there is one general statement regarding those isomers is that trans isomer is generally more stable than cis isomer. The reason behind it, if you observe the structure of cis isomer, the bulkier groups are nearer to each other. They create lot of steric interaction, and once the steric interaction present, there is a increase in the internal energy, and once the internal energy increases, the stability of that molecule goes on decreasing. And if you observe the trans isomer carefully, you will find there the two bulkier groups are well separated from each other. There is no question of steric hindrance, no crowding, and therefore no question of internal energy. The energy always associated near about as a zero, and therefore trans isomers are generally more stable than the cis isomer. And now E and Z, when such carbon-carbon double bond is in a complicated system, we cannot identify whether the compounds are E or compounds are cis or trans. And to avoid that complication, to make the nomenclature system simplest one, the scientists invented the new system which is known as a E and Z, that is based upon the priority number, and that priority numbers 1 and 2 are again applied or used according to as a sequence rule. And as we know that sequence rule are formulated by 3 scientists. In short, it is also known as CIP rule. C stand for Kahn, I stand for Ingold, and P for Prelog. There are four rules. Number 1, atomic number. Number 2, next atom. Number 3, double bond or triple bond. Number 4th one is isotopes. So these are the certain what we can call it as a, and by if the priority group 1 1 are on the same side, that is known as a Z configuration, whereas if similar priority group are on the opposite side of the carbon-carbon double bond, then we can call it as a E, means across the carbon-carbon double bond. So that is the. Now let us see the second reagent over here. Second reagent will be NaOAC, sodium acetate, then sodium periodate, NaIO4, then NaIO4, ethanol in presence water, ATOH in presence of water, then it is 19 hour is heated at 70 degrees centigrade, and the yield is obtained near about 79% from compound number 1. So now let us look at as a reagent number 3. The reagent number 3 will be this one, pyridine. Py got as a pyridine, which is basic in nature. Then MsCl, methyl chloride. Then DCM, CH2Cl2, dichloromethane. It is near about is a 12 hour, and the temperature is kept 0 to room temperature, 0 to room temperature. And now let us look at as a reagent number 4th. The reagent number 4th are saturated NH3 ammonia in methanol in MeOH. Then next one again CH2Cl2 dichloromethane, 5 days required to complete the reaction at room temperature, and the yield is obtained about 76%. Now the reagent number 5 will be Me3N trimethylamine, tertiary amine, then iodine I2, then CH2Cl2 dichloromethane, then dichloromethane 2.225 hours heated at 2 to 5 hours kept at minus 20 degrees centigrade, 50 degrees centigrade, and they got near about as a 83% as a yield over there. These are the 5 reagents how we are getting as a glycosidine diazerine that we have seen here, and remaining the another diazerine how we can prepare, that we will see in the next lecture. With this, let us stop today here. Have a nice day. Thank you.